Hey guys, welcome to day 14. Um, Today the first piece will be very simple. It'll be an extension of something you probably already know. The second piece is going to be the biggest piece of the algebra portion of limits. I warn you now, if you struggle with factoring, or multiplying, or distributing, today and tomorrow will be very interesting days. Because if you cannot factor or FOIL or distribute correctly every time, there is a chance that you will struggle with some of these materials. It is not because the materials themselves are difficult. It is because if you can't make these steps, you have to do them with the numerical approach, or you have to do them with the graphing approach. And for some problems, I will not allow that. For example, on your quiz, the next quiz we will have will be over limits, specifically. And on that quiz, you will not be allowed, on some questions, to give me an answer that is found numerically. You have to do it the analytical way. Now, you can check your answer with a graph. You can check your answer using the approach where we get closer and closer to the number. But the work I better see had better be work that it deals with how we do it the analytical way. Because both pieces are necessary. There are some problems that you can't just plug into a calculator and get an answer to. In fact, there are still problems out there that computers today can't solve, but mathematicians can, because they just do them in a different way that isn't solvable with a computer. Or maybe it takes an extraordinarily long period of time for a computer to solve, on the terms of hours or days or weeks. Okay? We like to think that computers are really fast, but some calculations take a long time if you're doing them by hand with the analytical approach, or with the numerical approach, or with the graphing approach. Like, some just don't work well. So, let's take a look. The first thing we're going to talk about is theorem 1.6. It deals with trig functions. Now, if you haven't taken trig yet, I'm sorry. We'll have a trig day next week where we go through like the big things of trig that you need to know. For now, for today, if you haven't taken the trig portion, a lot of this is going to be calculator work. But we will discuss probably on Wednesday of next week. I'm not sure yet. We will discuss like the big elements of trig you need to know and need to have down if you're taking calculus next year. But that'll be next week. So let's take a look. First off, the first piece of your homework is pretty straightforward. It might not actually be physically first in how I write them out, but it is the first part of your homework. Theorem 1.6. This is limits of trig function. Now, these are meant to expand our current understanding of how to do limits. Because remember, as of right now, there are only 3 limits we technically know how to do. Oops, should be fine. We can do the basic limits. We can use the properties of limits to define more advanced limits, and then we can use things like rationals, radicals, and polynomials to find more limits. But those are the 3 basic lists. If it doesn't fit into one of those categories, you can't do it yet. But here, you're going to see that for a lot of these, there's basic things that are very simple. For example, there are 6 basic trig functions, and for all 6 basic trig functions, you may essentially plug. So for sine, if you're going to x, you can essentially plug in x. For cosine, same thing. For tangent, and then for the 3 advanced ones. So limit x approaches c of cosecant is cosecant c. Limit as x approaches c of secant is secant c. And then limit x approaches c of cotangent is cotangent c. And so for all the trig functions, trig basically becomes a plug and chug. Now again, this allows us to do more advanced mathematical processes because we can not only do the trig ones, but we can also do ones that have trig in them. For example, take a look at these 3. the limit as x approaches 0 of tangent of x. Next one, the limit as x approaches pi of x cosine x. And then third example, limit as x approaches 0 of sine squared x. Okay. Now I'm going to use the properties to solve all of these. And when I do so, I'm going to try to limit or display the theorem as well. So let's take a look. First one. I can use here from theorem 1.6. We know that according to theorem 1.6, if we have the limit of tangent, we can just plug it in. So this would become equal to the tangent of 0. And then if you know tangent of 0, it's of course 0. But if you don't, you could use a calculator and get the same result. For all of calculus, make sure your calculators are in radians. I've taught calculus for a number of years now. I have never seen a calculus problem that isn't in radians. So make sure your calculator is in radians for everything you do. Okay? This one. First thing I'm going to do is I'm actually going to use one of our old theorems. This is one of our properties. This was theorem 1.2. And this was the multiplication or product. So I take this single limit, which contains two pieces, x and cosine x. What I'm going to do is I'm going to write it as the limit as x approaches pi of x times the limit as x approaches pi of cosine of x. So this is our product property from theorem 1.2, which says that if I have a product inside the limit, I can take the product of the limits. So this allows me to do the left one by using theorem 1.1. Theorem 1.1 states if I just have x, I can just plug in pi. So pi. On the right hand side, I use theorem 1.6. Theorem 1.6 says, what if I have cosine? I just plug in c. So this becomes cosine of pi. Now, if I'm honest with you, most of the time, you'll learn to jump from here to here. Know that these properties exist and allow you to do this, but realistically, we're going to do this. Okay, now, pi is just pi. Cosine of pi is -1, and pi times -1 would be negative pi, meaning that's my solution. And again, I could verify this with a calculator if I wish to. This bottom one, bottom one is the fun one. For this one, I'm going to use theorem, I believe it's 1.4. Nope, 1.5. Theorem 1.5. Theorem 1.5 states that if I have a function inside another function, I can rewrite the limit inside the previous function. What this basically means is sine squared x is sine of x squared. So what I'm going to do is I'm going to take this limit, which used to be applied to the whole thing, and now apply it just to the sine part of it. So what does this become? This becomes the limit as x approaches 0 of sine of x squared. Notice I cannot take this limit. This limit is impossible. I have nothing that gives me, like, this isn't sine squared, so I can't just plug it in, but I can do this one. This one is doable. It's a subtle thing. You have to start seeing that for some problems, the way they are written right now is not acceptable. I cannot do this problem. I can do this problem. And the fact that they're the same thing is important. I cannot do this limit. But if I rewrite it, I can do that limit. So let's do this. On the inside, we'd get sine of 0. And the outside we still have a square. Sine of 0 is, of course, 0. And squaring that gets us 0. Make sure you're able to take those functions and get those steps. Now, I know many of you are looking at that and might say, like, Douglas, if the end result is the same, why can't we just plug it in? And the thing is, mentally, yes, that's what I do, right? If I'm doing this problem by myself, I'd be like, okay, plug in 0, done. But the fact of the matter is, the only reason I can plug in 0 and get an answer is because of the properties that let me plug it in. Okay? I'm not really plugging in 0, I'm applying 0 to the sign and then afterwards squaring it, which is a different step than what I was originally given. Despite them giving me the same result, they are different. So make sure to note how they fit together. Now, this next part is the part where we actually have to do some real math. Theorem 1.7. Okay? This is referred to as functions that agree on all but one point. Okay. For this one, I will actually show you how the textbook writes this function. And, well, because I don't feel like writing this. So let's take a look. Okay. This is Theorem 1.7, as written by the textbook, and I want to go through it kind of slowly and see how we talk through this. Let C be a real number, so you notice that C is the number we're going towards. Let f of x equal g of x for all non-C values. So, let C be a real number, and let f of x equal g of x for all non-C values. Now what this means, we'll get to in a moment, but this means that there's an algebraic step we can take to determine f and g. Now, this has to be over an open interval that has to have C in it. Now, if the limit of g of x as x approaches c exists, then the limit of f of x also exists, and they are the same thing. That's how you read a statement like this. If the limit of g of x as x approaches c exists. So if this limit exists, then the other limit has to also exist, and they have to be equal to each other. I want you to take a look at this problem. We're going to do this problem here, and I'll showcase what this really means, but you can see as we go a little farther down what it actually looks like. What it means is we need to find g of x. And g of x is an equation that is similar to f of x, except at one spot. Let's take a look. So my equation is, we're going to find the limit as x approaches 1 of x cubed minus 1 over x minus 1. Now, first thing I want to point out, if I just try to plug, it doesn't work. Why? Because I end up with 0 divided by 0, and that's not allowed. I cannot divide by 0 ever. Ever. If I plug in 1, I get 1 cubed minus 1, so 1 minus 1, which is 0. And then on bottom, the 1 on top is fine. The 0 on top is totally fine. On bottom is the issue. If I try to plug in 1 here, 1 minus 1 is 0, and I'm never allowed to divide by 0. This 0 is the problem. So, what do we need to do? Step 2. We're going to find g of x similar to fx. How do we do that? We're going to factor f of x and cancel, if possible. Let's take a look at this function. I'm going to write it down here, the limit as x approaches 1 of x cubed minus 1 over x minus 1. What I can do is I am allowed algebraically to rewrite this statement using something called the difference of cubes formula. Difference meaning subtraction, cubes meaning cubes. So what does this become? We end up with the limit as x approaches 1. Now on top we'd have x minus 1 times x squared plus x plus 1. On bottom, we'd still have x minus 1. Now these two are exactly the same expression. These are exactly the same. In fact, if we were to type these into a calculator, these would look exactly the same because it's just factoring, right? Factoring doesn't change the problem. However, you will notice that there is an x minus 1 on top and an x minus 1 on bottom. What we can do algebraically is we are now going to cancel. Now when we cancel, this will actually changes the equation. Because while if I plug in 1 here, there's a problem. When I cancel, I will not have a problem anymore. Watch what happens. This is equal to the limit as x approaches 1. Now if I cancel the x plus 1 and the x plus 1, on top I end up with x squared plus x plus 1 over 1. Or obviously you could just write the top by itself. Now if I plug in 1, I do get an answer because it's a polynomial. Right, if I plug in 1, I get 1 squared plus 1 plus 1. These two 1s are from the limit, this one is from the equation, and I ended with an answer of 3. Here's the important detail, what this theorem 1.7 means. Let's pull that theorem back up again. Let f of x equal g of x for all non-c values. To help explain this, it's helpful to graph what these look like. So let's take a look here for a second. Right here. This was my original equation. This is my new equation. What do you notice about these two? Well, they look the same, except at one spot. Here, there's a solid dot. Here, there is an open dot. That is because at 1, this value is undefined, right? We end up with 0 divided by 0, not allowed. But this equation is the exact same picture except at c. However, this equation is much nicer to work with because this equation, when we actually do the problem, we get an answer, 3. Right? And in the graph, we get an answer, 3. And if we do the analytical approach, we get an answer, 3. These two are different equations, but they act the same in terms of their limits. This equation and this equation are different equations, right? But they act the same in terms of their limits. For some of your problems tonight, they ask you to find something called, they say things like, find g of x. Or they might say, find a similar equation. What that means is, we had x cubed minus 1 over x minus 1, and we found an equation of x squared plus x plus 1. This is our g of x. This is our alternative equation. Much easier to work with. And so if it asks you to find a similar equation, it just means to find this. It basically means, factor this and simplify. Now again, these two equations are not the same, but their limits are the same, and that's a big detail. Okay? You can write x cubed minus 1 over x minus 1. It doesn't equal. These two are not equal to each other, but they are similar to each other. Right? They are roughly the same, except at x equals 1. Right? This one cannot equal 1, but this one can. And so this is an alternative way to get us to an equation that we can actually solve by hand without needing to do the numerical approach or the graphing approach. Let's look at another one. Okay. Example. I took up a lot of space to write that, so I'm going to try to do it a little faster this time. Limit as x approaches negative 3 of x squared plus x minus 6 over x plus 3. Again, if I just try to do a direct substitution, plugging in negative 3 on top, plugging in negative 3 on bottom, I would end up with 0 divided by 0, not allowed. Okay? So I can't use the rational expression approach, where I just plug it in and go. So I have to find a similar limit. So limit as x approaches negative 3. This is where I said factoring would be important. On top, this factors into x minus 2, x plus 3. Now we can see on top and bottom we have the same piece, so we can cancel those. This becomes the limit as x approaches negative 3 of x minus 2. This is our g of x. Okay? It's a similar expression that again has the same limit, but not necessarily the same values. Right? I can't plug in -3 here, but I can plug in -3 here. And in fact, when I do, I'll do -3 minus 2. -3 minus 2 would be -5, and there's my limit. Now again, looking at our textbook, you can see this equation right here. Right, there's my limit. I can see this equation. If I actually try to get to -3, I don't get an answer because it's an open circle. But notice how it looks like a linear equation, and in fact it looks like this linear equation, x minus 2. This is our g in this case. G being, again, this similar function at all but one value, such that if the g's limit is equal to a number, then so is the f's limit. So if I can find g's, I automatically find f's. This gives us a huge advantage. This is the last thing I'll talk about. I'll do one more example before I do so. But here's how we look at this. These are your 4 basic strategies. 1. Learn to recognize limits that can be evaluated by direct substitution. These include things like your trig limits. These include polynomials. These include your rationals where the bottom isn't 0. 2. If the limit of f of x as x approaches c cannot be evaluated by direct substitution. So if you try to plug it in and it does not work, try to find that g. Which remember, in this case, my g was this equation, okay? It's a similar equation that should have the same limit. Try to find that g. Use theorem 1.7 to find it analytically, so that's what we did there. And then use the graph or table to reinforce it if you need to, but only use to reinforce. Don't use to substitute your work. Let's do one more. Which one do we want? Which one do we want? Ooh. Let me do one of your homework problems. That would be nice of me. Okay. So we've seen standard factoring. We've seen using difference of cubes. One of the other main factoring ones for your homework tonight, you have number 51. Number 51 states, do the limit as x approaches -4, oh no, sorry, as x approaches +4 of x minus 4 over x squared minus 16. Now, let's follow through our steps. Step 1. Can we just do the basic direct substitutions in theorems 1 through 6? No. If I plug in, I end up with 4 minus 4 on top over 4 squared minus 16 on bottom. This is being 0 over 0, not allowed. I can't do that. So I'm instead going to attempt to use theorem 1.7 to find a similar equation. X approaches +4. On top, x minus 4 is just x minus 4, but on bottom we'd have x plus 4, x minus 4. Note, you may end up factoring on the top, like we did on the previous problems. Right, this one and this one. You may end up factoring on the bottom, look at it here. You may end up factoring on both. It just depends upon the problem, so make sure you're comfortable with factoring. From here, we're going to now actually fix this limit by canceling. We then have the limit as x approaches 4 of 1 over x plus 4. Remember, this is our g of x. This is our alternate equation, right? These two are similar except at 4. This one answers at 4, this one doesn't answer at 4. Now, we actually do our math. Plugging in 4, 1 over 4 plus 4, which would be 1 over 8. Now, to verify this result, I'm going to use my graphing calculator. Alright, here's Desmos. My original equation was x minus 4 on top, x squared minus 16 on bottom. This is my original equation. Now check out my alternative equation. Now, just to verify, if I come over here to 4, right, I do not get an answer. Now let's go here. All right, my alternative equation was 1 over x plus 4. You'll notice that these two look exactly the same, but there's one major difference. On the red graph, right, 4 is undefined. On the blue graph, 4 is defined as 0.125. And remember, 0.125 is 1/8. And so this gives us a way to find these two equations such that they actually do end up giving us solutions for the limit. And again, if I was to do the analytical approach, or the numerical approach, this top equation would get me the same answer as this bottom equation at 4. Despite them being different graphs, because they have that one point that's not in common, it's just how it works. This is pretty unique, you know? It finds unique ways to actually get to a solution and use that solution to find an answer. Let's do one more. One more. I got a couple minutes to spare. This is not a homework problem. This is just another example. Let me see if I can make one up here. Let's see. The limit as x approaches -1 of x squared minus 1 on top over x cubed minus 1 on bottom. Sorry. X cubed plus 1 on bottom. Okay, if I plug in -1, I have -1 squared minus 1 over -1 cubed plus 1. -1 squared is +1. Minus 1 would be 0. That's not a big deal. 0 on top is not a problem. On bottom is a problem. And so I see that. I know this can't work. And so I should instead investigate an alternative limit. So, limit as x approaches -1. I factor the top. The top factors using difference of squares into x plus 1, x minus 1. The bottom factors into x plus 1 times x squared minus x plus 1. Now, I can use algebra to cancel the x plus 1 and the x plus 1. And what's left behind? The limit as x approaches -1 of x minus 1 on top and x squared minus x plus 1 on bottom. You'll notice that these equations actually allow me to plug in -1 now. So -1 minus 1 on top. On bottom, -1 squared minus -1 plus 1. So on top, -1 minus 1 would be -2. On bottom, -1 squared is 1. Double negative would make this plus 1 plus another 1. And with -2 over 3. This is an alternative way of just finding that limit. And again, I can get that same result doing it the numerical approach by plugging in numbers or the graphical approach. But if I don't have either of those as an option, or they're bad options, this approach works as well. One second. Okay. That is it for today. We did only 2 theorems, but they're 2 big theorems. Theorem 1.5 allows us, Theorem 1.6, remember, allows us to plug in the trig functions, along with theorems 1 through 5. This gives us a whole array of problems we can actually approach now. And in Theorem 1.7, we did out of the textbook, and looked at how to actually determine a limit using analytical approaches only. So no numbers, no graphs. All of these are tremendous skills to have for calculus, so make sure you get some practice on those tonight, and I will see you guys tomorrow.